Okay, let's begin. Welcome back, everybody. We're going to take on to this example in just a moment where we left off. And I said we're going to jump into the delta method, but we're going to do the central limit theorem first. And so, the preliminaries you might have looked over, they'll come in handy for central limit theorem as well. So if you did spend some time looking at Taylor's theorem, we're going to use it there as well. We're also going to have to go over moment generating functions. So I'm going to do this a little bit gently. We'll build up a little bit more mathematical speed in this class. We will be coming around to this example. Before I continue, happy Chinese New Year's to those of you that celebrate. I think any good reason to celebrate is a good reason. It's Year of the Tiger, and I'm a tiger. So just a quick question, how old am I? I'm 75. Yes, that's right. I'm 75 years old. I'll let you guys work on it. But that's definitely one of the two coolest Chinese zodiac symbols, tiger. So all the other ones are like pig and rat. So just looking at this, my wife is a pig. It's probably the only time I can ever get away with saying that. So I had a lot of fun with that when I looked that up. So needless to say, I'm in the doghouse. So I got myself in trouble with that. Anyway, Happy New Year's to you guys. So I just think that stuff is exciting. I'm looking forward to the time when we can all get together and celebrate. There usually is a very good festival around here. Hopefully next year we'll be able to celebrate all that stuff. Also, my TA, he's not quite ready to start grading yet. So I started doing some grading and I read over your definitions and I didn't know how to grade them, to tell you the truth. And I never know how to grade them. And I think I said I was going to go rather gentle on it. I'm not going to grade them at all. I'm just going to read them and I'm going to probably ask you to do this again at the end and maybe come up with something a little bit stronger, but really I just want you to be thinking about it. I wrote down some definitions and we can look at them. So I thought maybe the best way to handle this is just to write my own definitions down. Let me try to make this larger. We can read it together. I'll say a few things about this before we carry on. We're about to get into inference, so this will start to make more sense. So we start comparing different inferential paradigms. I want to point out something very important about inferential paradigms is a lot of them overlap each other in all kinds of places. So some of the definitions I was seeing, I was like, well, that's true for all of them. So it's not true that you know, for classicism, they only deal with relative frequencies or things like that. They define probabilities by 1 over the number of events. That doesn't make it classicist a classicist. A lot of statisticians will use that. So base things off of relative frequencies. I see frequentists do it. I see Bayesians do it. And so we'll see an example where we all do that in the future. So anyway, it is difficult to come up with these definitions. Let me just briefly read through some of these, and I'll post these to Slack later on, and you can read through them as well. Classicism, it's not entirely clear what this means. So in any discipline that they call classical anything, all they're saying is it's not the modern thing. So if I say I'm a modern statistician, it depends on when I say it. So that's not a very good statement either. You'll see these old 1960s stat textbooks that say like modern statistics. So it's like, oh, well, that's not a very good name either. If you were saying you're a modern statistician these days, you're probably saying that you like neural networks and you like computation and you like forecasting and all the current trends. So semi-parametric functions. In this class, we're kind of doing a rather easy treatment of things where we do make all these parametric assumptions. And we're not getting into super fancy stuff, but we'll try to fancify to some degree and make it a modern class. But classical stuff, it's not clear what it means. So classical statistics is much the same as in any other field. It just means old, and we don't know how far back we need to go. We don't need to go back very far in statistics because it's a relatively new field. So I'd say stats wasn't a thing until the 1900s. People were kind of doing it, and there were some designs, and there were some experiments, and there were some estimations, but it wasn't formalized. And so probably wasn't until like the 50s that we started to get really formalized in what we were doing. So that's all really new. That's good for us. That means there's a lot of positions and a lot of places for growth. So we're still deciding, what constitutes statistics? What games can we play? What makes it formal enough to be in a department like this? So I would say these paradigms are defined by techniques that people use. And so sometimes it's better to just look at different techniques, look at examples. So I'd say much of classicism is dominated by frequentist stats because that's kind of what was coming first. That view where we formulate a test statistic and we see what its properties are if we recollect samples over and over and over again. Or if we're trying to come up with some technique, it's going to have some frequentist property. Discuss that in a second. But I would say there's all kinds of stuff that are classical which aren't frequentist as well. So maybe ridge regression if you're familiar with that. So penalized regressions, it's not clear what the frequentist property is there. So, but I would say things like ridge regression if you're familiar with it, Bayesians do it as well. So that could be a Bayesian technique so long as you derived it under a Bayesian lens. So a lot of it has to do with what you're thinking about in the process of deriving something. Which properties are you assured of? And there can be overlaps. Any sort of penalized likelihood technique I think is a good idea. Bayesians do it in a particular way, but classicists have been doing it for a long time and it's not necessarily frequentist. So I would say it's not well defined what classicism means, even though you'll hear a lot of people say it. It certainly doesn't mean non-Bayesian. So even though I think a lot of people do mean that when they say it, but we want to be more careful in this class. I should mention penalties can also be chosen to make frequentist connections. So frequentism, it's all in the name. There's something that we're monitoring and we're looking at its frequency. So for instance, confidence intervals are a frequentist tool. Bayesians could derive them and come up with the interval. The intervals have this property that whatever the interval is based on should be covering that true parameter at some nominal rate. So if I say it's a 95% confidence interval, then I mean that my interval covers 95% of the time, but not quite. So you could be an asymptotic frequentist. And this might be getting better and better as n gets bigger and bigger. Or it could be exact for your sample size. So you even have to qualify what kind of frequentist are you? And are the frequencies you're reporting, are they accurate? And people that don't do that, when I say, they say, well, I'll ask them about their interval and they'll say it's 95%, and I'm like, well, what does it actually cover? And if they say they don't know, I don't think they're a frequentist anymore. You're not actually a frequentist, you're like a fingers crossed. So sometimes we report that something asymptotically will cover 95%, but for your sample size or for your model, it might be 82%. It might be 12%. And if you didn't check, I don't think you're an actual frequentist, I think you're just using words. So we want to mean something. So again, I'll post these with all my notes of caution, personal notes I put in here. So I do say, while a majority share Bayesian, there's many ways to skin cats, lots of ways to derive things. I should say, I utilize frequentist methods all the time. So especially when I'm diagnosing my Bayesian MCMC code, I always use frequentist techniques to make sure that I'm doing it right, because I can keep running it over and over and over again, and I have mathematical properties that I can monitor. And if my code isn't doing something I know is supposed to happen in some frequentist sense, I know I have an error in my code or my mathematics is wrong, something like that. So conjoining these fields, I think, is really what we want. Fiducialism is just a mistake. So that's what I should say. So it's an old branch. You don't hear people talk about it too much. I did see a paper that was written some number of years ago called The Correct Fiducial Argument. So this is one of Fisher's blunders. And in a nutshell, what Fisher said was, I can take the likelihood function and automatically upgrade the parameters to random variables. And you cannot do that. And there's no magic wand for doing that, but there is a probabilistic tool for doing that, and that's Bayes' theorem. And so this is the way that Fisher got some Bayesian properties without specifically using Bayes' theorem. So he had this automatic upgrade to a random variable. Everybody understands that's wrong now. Fisher understood that was wrong, and he said, maybe what I was trying to do was Bayesian. Let's move on. A lot of people accused Fisher of taking the likelihood and multiplying it by 1, which would be the prior, which is an improper prior on most parameter spaces, and not telling you he did it. And Fisher got pretty grumpy. No, I did not multiply by 1. How dare you accuse me of such a thing? So, you know, these are really counterproductive arguments, and I think really what we want to do in this class is compare methods and see how they work. I kind of do like these guiding lights in principles, and we'll discuss some of them in chapter 6. I don't like them for argument's sake. I like them because they help me to think about what I want when I'm trying to derive something. And some methods have these sort of constraints built into them. I do like the likelihood function. That doesn't mean you have to be a Bayesian to use it. A lot of people use it in different ways. So I will say later on in this class, when we get into hypothesis testing, Neyman and Pearsonians use likelihood functions to derive test statistics that are uniformly most powerful, that have good frequentist properties. And they use the likelihood function in an entirely different way than a Bayesian would. And so there's something called the likelihood principle, and it says that if your likelihoods are proportional to each other in 2 experiments, then you should come up with the same inferences. But what we don't talk about in statistics is how you go about business once you have the likelihood. What estimator are you going to pick? And there's more to that conversation. So we need to discuss decision theory. So I think we need to get a lot more specific than just these very coarse definitions. But again, you can read through these and kind of just have them digested. What are these things? So I think the correct fiducial argument is be a Bayesian. So of course, if I said this to an old fiducialist, I bet I just set off a debate. So anyway, nowadays we have computation, so I think we argue a lot less about epistemology, what our beliefs are. So we demonstrate. I think that's a better way to go about business. Okay, enough about that. Back to our example. So we had simulated this. I won't run the simulation again. But we're looking at this example where xi's are uniform between 0 and alpha. What I did is I sampled n data points out of this. Out of this distribution, I took the min and the max. So this is the min, the max, and I computed the range and the mid-range. So same thing we've been talking about for weeks now. And once I have the range and the mid-range, that's just 1 point. Then I go out, I collect n more samples, I redo it again, compute these statistics, and I compute another point. And we see this triangular shape of all. And that's the joint distribution of the range and the mid-range. Just real quickly, this is not a question that we're going to specifically formalize in this class, but I do like to ask it. If you could only have the range or the mid-range, and I asked you to estimate alpha, which one would you want? Turns out I would want both of them. But, and you couldn't do any better, I would really want the maximum. And we'll be getting around to that later on, and we've seen that. But if I couldn't have it, which one would you want, the range or the mid-range? I think we've answered this question before. I'd take the mid-range and multiply it by 2. It turns out it creates a better estimation of alpha, but they both estimate alpha. So the mid-range divided by, multiplied by 2 is just the sum of these 2 things. And it's basically the end point, which is approximating alpha, plus some estimator of 0. You know, I'd rather plus that estimator of 0 than subtract it, because this is just making your estimate more biased. And so it's also incurring more variation as well. And so all properties we'll be coming around to in this class and thinking about. We'll see some related problems to this problem throughout the book, and that's why we're studying it. I don't think that this has a lot of applications, but it'll at least get us through some probability mechanics. Okay, so that's that distribution, and we see that triangular shape of all. We want to pick up there and build that distribution explicitly. I'd like to write down, if I could, the density for that triangular distribution. That would be nicer. If I couldn't do that and I couldn't understand it mathematically, I guess I would do this simulation, but it's rather expensive to do that. So if I could just figure out what that function is, you're better off doing that. If I couldn't do that, I still have a lot of clean insights from simulation studies. It just takes computation time. Okay, so we had derived this before. This is the joint distribution of the max and the min. And it's just that thing right here. So we wrote this down last time. This is in your book. And there's some constraints, and we better be specific about those constraints. So these constraints that are enforcing that triangular shape and everything. Here's the forward transformation. We're trying to get this distribution for R and V. In the inverse transformation, solving for x1 and xn, we did last time, and there it is. So I'm just going to rewrite these inverse functions. This is the key to seeing that triangular shape. We wrote down last time, we were able to convince ourselves real quickly that that triangular shape was there. I'll just walk you through this, but you probably want to check a little bit more specifically. I will mention I'll never give this to you in like an in-class midterm or something like that. So I don't want you fussing with that stuff and messing up your whole exam because you can't figure out what the boundaries are. So I'd never give this to you on an exam, but it's still good to think through these problems. So the range right here, I'll say what I want. This is going to be when xn is equal to alpha and x1 is equal to 0 right here. This will be, I'm going to call this the mid-range, and this is the range right here. So this is going to be alpha. And this will also be alpha. Okay, so I think what we convinced ourselves of real quickly is when this is xn is equal to 0 and x1 is equal to 0, the range is 0. So the mid-range is 0. So that point lives on this space right here. This happens when xn is equal to alpha is equal to the minimum. And so the mid-range is alpha, and the range is again 0. So that lives in my space right here. This point also lives in the space, and I can convince myself real quickly there's only one possibility when the range is alpha, and it's that. So I don't think I need to convince you any more of this. What I could realize if I were a freshman or a sophomore, or whenever you end up doing this, and I needed these bounds real quickly, I would just grab those 3 points. And I would convince myself by looking at these equations, these are linear equations. And so the relationship between V and R is linear. And so there's only one way I can do that. And I would be done. Of course, that wouldn't satisfy you if you'd never seen this before. So that's just something I would do real quickly. What I would probably also do, once I did that, is I would probably grab a couple points in space and plug them into the relationships and see where these relationships fall. And so that's what I used to do back in calculus classes. I would just grab different points in the space and work through everything. I guess if I were trying to write a paper and I wanted to be really sure, I'd probably do this. But there's an easier way. So if I just grab those inverse functions, and I guess I'll write it out as v is equal to, and I'm going to rewrite it two different ways. So I'm going to write this is xn minus r over 2. So I just grab this first equation right here, solve for the mid-range. And we also have the mid-range is going to be x1 minus plus r over 2. So I'm just rewriting those equations. And so I like doing it this way because we just happen to plot this in terms of the mid-range, which we're calling v for some reason. So then I can just see this relationship. If I thought it was like this, I would probably model it like that because it's an easier relationship than spinning this around, where I have to break this into a I have to break it into two functions to describe everything. And you probably have seen that in the book. Here's what I do to figure out where the bounds are, is I just start thinking about limits of everything. What can I move around? This is max at alpha. So xn is maxed at alpha. This is going to be less than alpha minus r over 2. So I just convince myself of all these things that I can move around in the equation, and I think about which bounds they form. So I'm just trying to express this relationship right here. And that's what that line is. So this is alpha minus r over 2. And I can do the exact same thing over here. I can think about this in terms of x1 if I played around with it, that this could take on any value. And so I haven't absolutely constrained what r is just by wiggling around x1. So this is true. That's that line. And this thing right here, the minimum of x1 is equal to 0. And so I can rewrite this, that this thing right here, and again, I'm adding that in. So I just think about the direction as I end up flooring this thing towards 0. This is going to be greater or equal to 0 plus r over 2. R over 2. I don't have any better insights than this. This is how I go about it if I got one of these problems. And I will say, in all of my years of being a graduate student and working in the tutoring centers, I messed up one problem that somebody came in. And I said, you got to come back tomorrow. I've obviously messed something up. This stuff doesn't add up to 1. When I did my sanity check, and it was one of these. The bounds were wrong. So it's probably one of the easier things to mess up. You just need a lot of different ways to verify everything. So this is how I do it. This right here is r over 2. That's that line. You have better methods, then good. Sam, do you have a better way to explain it?
Yeah.
Something.
That's how I would do it.
Cool. Okay. Anyway, I try to write it in terms of whatever the easiest thing to graph is. Let's just say a few things more about this solution right here. So I guess if we want to complete it, we do need the Jacobian, and then we just need to plug everything in to our formula. And so let's just write that out. So the Jacobian, for our transformation, we're going to use these inverse forms, and we're going to take its partial derivatives. So this is going to be the absolute value of a Jacobian right here. We did have a nice discussion about this in transformation of variables in the review session. So if you want to know more about these formulas, and we'll probably come back in the next review session and go over these formulas in a little bit more detail. I'll give you some nice transformation problems on the next homework to provoke you and want to see, wait a minute, do I really understand where these formulas are coming from? So this is the stretch factor when you transform everything. It's how the space stretches. So that when you're integrating over everything, you end up mapping that space directly. So this is just d, I'll say xn, dv, I'll say dx, n, dr. And the orders of these things are arbitrary, but once I've assigned the rule to what I'm taking the derivatives with respect to, I need to follow that order everywhere. So this will be my other random variable, dx1, and I have to do these in the same order. If I did permute these columns and the rows, I would introduce a negative sign into everything. When we take our absolute value sign, at the end of the day, those will cancel. So it doesn't matter how you do this. I will also say the Jacobian term is the chain rule in something like a U substitution, which you learned in your first calculus class. And so if you don't see this exact rule out of that, go back, think about that, and if you want to discuss it more, we can do it in the review session. So let's take these derivatives. Derivative of the match with respect to the mid-range, that's 1. Derivative of the min with respect to the mid-range, that's 1. Derivative of the match with respect to R is a half. And this last one is minus a half. So I just take my determinant of this. So that's going to be minus 1/2 minus that thing, 1/2. Again, I'm taking the absolute value of this. And so this turns out to be 1. Minus a half, minus 1, absolute value, that's 1. So that's nice. If we had forgotten to take the Jacobian, we would have gotten the right answer. But if you did this on an exam and I saw that you didn't actually go through and verify something was 1, you'd lose some points there. So we're almost done. So all I need to do is take this formula and re-express it in terms of R and V. And so I'll just rewrite this. So this thing right here, R and V, this is going to be F, X1, X2. I think I got so sick of writing the X1 and the X2 and it bothered me because that notation is already used that I ended up leaving these braces in here. Times the Jacobian. It's this thing right here, but I'm going to write these is a function of R and V. So I'm going to express these using the inverse transform. I'm going to multiply by that Jacobian. So that's just going to be n times n minus 1 over alpha to the n. I'll take xn and I'll plug in what it is. This is going to be v plus r over 2. That's x1. That's xn. Minus whatever x1 was. So that's going to be v minus r over 2. It's raised to the n minus 2 power. And I need to be specific about my bounds as well. I'll write those down in a second. But this thing right here, v minus v, there's no v's in there, r minus 2 minus a minus r minus 2, that's 2 r minus 2's added together. So that's just, oh, and I did change my notation. I was calling this little r. Right here. So I'm just trying to distinguish the functional arguments in the random variable. So that's just r raised to the n over 2. And then I need to tell you where these things live. It's easiest to describe these in this direction where r goes between 0 and alpha. And then I'll say my mid-range goes between r over 2 and alpha minus r over 2. That's it. The book likes this problem. I like this problem. We'll be using this a lot. The reason the book likes this problem and I like this problem is when we go to infer alpha, it lives on the boundary of the space. Makes lots of interesting issues to discuss. So we'll be thinking about this later on. So that triangular shape and the density of those points can be expressed using this formula. And if you knew different sampling techniques, sampling that picture and creating those samples, I can use this formula, this density function to do it, and do it much faster than I did in my earlier simulation. This isn't a class on sampling, but you will be exposed to it. So in the next homework, we'll have some sampling problems as well. Okay. The book says, so just a little bit more. So if we wanted to look at, so we can look at the density function for R and the density function for the mid-range. So this will be the integral of n minus 1 over alpha to the n, r to the n minus 2. And I'm going to have to integrate over dv, my mid-range. And I can do this using these bounds, r over 2 and alpha minus r over 2. This integral is a little bit harder just because of the way we have to break everything up when we integrate out r. And so you'll have to go back to your picture and see how to break up that integral. They do it in the book, and you can look at those functions. So this is similar. It's in the book. You can look through that. I'm not going to do it because we're never going to touch it again. So, but we will look at an integral that's very similar to this one later on in chapter 7. So I think it's a good idea that we just write down what this distribution is. And it's the easier integral to solve. So this couldn't be any easier. This one you have to split into 2 chunks to integrate over that space. But this is going to be n times n minus 1, alpha to the n, r to the n minus 2. There's no mid-range in there, so mid-range pops out. And I'm going to end up integrating between r over 2 and alpha minus r over 2. So I'm just evaluating v at those. So this is just n minus 1, alpha to the n. And this is going to be alpha to the r over 2 minus r over 2. So this is going to be those things added together. So I'll just write this down as minus r. And I forgot my r to the 10 minus 3. I have to remind you where r lives. It lives between 0 and alpha. And they make a point to show you this is a beta distribution. So I wanted to take just a moment to talk about beta distributions because when we get into Bayesian analysis, this is going to be our first example. So just to acquaint you with this distribution. So again, we'll come back to this distribution. This will get used. The other integral, we'll never see it again in this class. Might be a fun exercise to go through if you want some calculus practice. It's not too difficult. say note. This is a beta. Density. So I'll say typically the way we write down betas, you need to do a transformation to see that this is a beta. But let me just show you what a beta density looks like. We usually have two parameters. So these are numbers that are greater than 0. They're positive numbers. And we'll get a lot of experience with this distribution, and this distribution is remarkably flexible, and the formula doesn't really show you. But it's usually a distribution defined between 0 and 1. And I'll point out that while R is defined between 0 and alpha, this is just a scaling of everything. That if I take something that lives between 0 and 1 and multiply it by alpha, it'll live between 0 and alpha. So this is just a beta distribution that's written down in disguise where I've rescaled everything to alpha. We can see that in a second. So beta distributions make these really neat distributions that live between 0 and 1. That one's not super neat looking, but this distribution can look like this, a straight line. It can do all kinds of things. It can inflect like this. So again, this is going to asymptote right here, or it can be incredibly skewed. I will simulate these for you when we get into the Bayesian section. So these look like this. So this is going to look like p to the alpha minus 1, 1 minus p to the beta minus 1. P is going to live between 0 and 1, and alpha is going to be greater or equal to 0, and beta is going to be greater or equal to 0. You cannot have both of these equal to 0. I'll just point that. So we'll just be nice and say they've got some. Let them be greater than 0. These really should be strictly between 0 and 1 and not on the boundaries. Otherwise, we're not going to be describing something that's very random. So you'll always end up getting the same realization back. Okay, this distribution also has a normalizing constant. So this normalizing constant, oftentimes we write down is some squiggly beta. I'll just write it like this with these two parameters right in here. Where this thing is just the integral over the kernel of this distribution. So this thing that we're expressing in the denominator is just a normalizing constant. So this is called the beta function. It does have a relationship to gamma functions. So you can express it as gamma of alpha plus beta divided by gamma alpha times gamma beta. If you don't know that, that's fine. You'll never use that. So I don't think you'll need it in this class. But it really is, it's just this integral. The neat thing to recognize is typically, unless alpha and beta were integers, you can't express this in closed form. So if alpha and beta are integers, you can write down exactly what this number is, and otherwise you have to approximate it. Okay, so just a normalizing constant. So pretty neat distribution. This distribution is the same thing. And so if we just take p times alpha, we let that equal to r, we end up just figuring out dr dp this absolute value is just alpha. And we go through and we transform, so anywhere I see an R, you're going to substitute in P alpha. You'll end up you'll end up using this as the Jacobian term, and what you'll get at the end of the day is that thing really is a beta distribution. So it's just all rescaled. So you'll get that extra Jacobian term right in here. You'll have the alpha to the P times alpha in here, so you'll get n minus 2 alphas. You'll get another alpha in here that you can factorize out, and it'll cancel all those alphas. They work through this in the book. I would encourage you to look through it and convince yourself that that is this in disguise. So I'll leave you a little bit of work. Okay. Trying to remember what time we end. 9:55?
Yeah.
Cool. 8 minutes is enough. Let's start something new. So we've seen order statistics, we've played around with them. This won't be our last experience. We'll be using them throughout the class. So read through all that stuff. I'll try to give you enough homework problems to cement it in your memory, but the more you do, the better. This is probably the most important result in classical statistics. It's probably the foundational result. So it's used all the time. It's not the only thing going, but it's something that is so good that we still use it and we talk about it all the time. Unfortunately, we also abuse it. And so in this class, we'll see in some cases where this can be abused. So central limit theorem. I'm going to say this wrong first and see if you guys can pick up on the little small nuances, and then we'll fix this up. So, informally, then we'll write it out more formally. But I'm going to show you the way people use it so that we can go back and forth. Use it in things for estimation tools like the delta method and see how it actually employs it versus just a theorem. So informally, it says something like this. If xi's come from some density, some distribution, okay, so this is just random realizations. There are versions of this for non-IID stuff, but we're going to make this IID. And we're going to give you the weakest version of this proof too. So we'll mimic the proof in the book, but I'll tell you more about more complicated proofs. So let xi's come from some density right here, so some distribution. We've worked with a 3-modal distribution before. We've computed x bar from it, and we saw that it was roughly normal. And that's about what the central limit theorem is saying. So what it says is that my sum of the xi's over n, I goes from 1 to n. This thing is distributed normally with mean mu and variance sigma squared over n. This is not exactly what the central limit theorem says. So math junkies in the room, hold your horses. We'll get this right in a second. So where the expectation of x is mu and the variance of x is sigma squared. Okay. So the central limit theorem does not quite say this. So for big N, so N is big, this is roughly true. Approximately, this is what we always do when we use it. So we compute that, and we maybe use it to figure out what the mean of this distribution is, do a pivot or something like that, whatever you want to do with it. The reason that this isn't exactly true is if I go to take the limit of this right here, so this thing we usually call x bar, I'll put an n in there just to denote that it's a function of n. So if I take a limit with respect to n, we know from the law of large numbers this is converging to mu, right here. It's getting really close to mu. If I take a limit over here with respect to n, there's only one n. And so this is going to be something that's fixed and finite. So I need to say this exists. What I mean is that sigma squared is less than infinity. It doesn't blow up. So not like a Cauchy distribution where the variance doesn't exist. If I go to take a limit over here, this collapses to 0, which is not a random density. So that is all correct. Saying that, that's not what we want to express. The formal thing that we want to write down is this. So formally, what we really mean the x bar n, so function of n, divided by sigma over root n. So limit n goes to infinity. This thing is going to converge to a normal 0, 1. So this density right here looks like 1 over square root 2 pi sigma e to the minus 1/2. I'll just write down whatever this random variable is, x bar n squared. There's no mean. The mean is 0, the variance is 1. So there's a 1 right there. So it follows this shape. So again, this is not quite right, even though we use it all the time. We say, oh, x bar is about normally distributed. But where the limit really comes in is we pull them all over to the left-hand side. So this is converging to mu. This is converging to 0, so I have a 0 over 0 situation. This isn't converging to a point. It's converging to a distribution. And so that's a concept that a lot of people have a hard time with. That usually they think things converge to a line or something like this. What it means is if I go back to this and I have relatively large n and I go and collect these samples, they're going to look like some normal distribution. They're going to be normally distributed. And so this result will hold as n goes bigger and bigger and bigger. This will be normal 0, 1. So if I took random values and I took n getting as big as you want and even bigger, and I computed this right here, and it's going to be normally distributed with mean 0 and variance 1. That's a surprising result. So it's basically just jumping around. The only thing you need for this to be true is that a variance exists in the distribution. That's all you need. To prove this statement with just that one fact is a rather long proof. And in fact, on my bookshelf at home, I only have a proof that I can dig up in 2 seconds. It takes about 2 pages of math to work through. Where the fourth moment exists, this is basically saying the second moment exists. So this is the expectation of x squared minus the expectation of x all squared. So if these first 2 moments exist, then this result holds. In your more complex measure theory books, they'll probably make a proof and they'll show that this converges in the strongest sense that you can think of and say if the fourth moment exists, we can prove this. Working through this with just this assumption is rather difficult. It would take a lot more than 2 or 3 chalkboards to work through. And so if you want to go conjure up that proof, you can do it. I've seen it before. It's pretty long. What we're going to do is we're going to make some other assumptions. We're going to assume that all the moments exist. That's a little bit too hard of an assumption for where this actually holds. We don't need the full set of moments for this thing to work, but it makes the proof relatively easy. So we're going to assume that. If you don't like that, you can study Fourier series. So that's the characteristic transform. And if the characteristic transform exists, you can do a very similar proof. Again, we're not going to do any hardcore proofs in this class. Nothing measure theoretic. You can look through what the book has. I'll discuss it a little bit more. If you want a distribution where the central limit theorem holds, but moment generating functions don't exist, think about like a T3 distribution. So a T3 distribution doesn't have a moment generating function, but it does have a characteristic function. Again, we won't be going into all those details. But what I'm about to prove, there's a stronger proof, and we'll keep that in mind, but we'll at least know the weaker proof. If you haven't done this already, study up on moment generating functions before Monday, because we're going to invoke them, and we're going to invoke some of their properties. The most important part to pay attention to in this proof is what happens to the remainder in everything. We're going to spend a lot of time discussing the remainder in everything. I'll see you guys on Monday, and we'll pick up there. Have a great weekend.